Sorry, miss. Okay, so here we go, guys. It says, example 1, use 5 rectangles of equal width to find an approximation area of the region lying between the graph of negative x squared plus 5 and the x-axis between 0 and 2. So I'm going to draw, I'm going to sketch, I'm going to exaggerate it. So here it is, me exaggerating it. There it is. That's the equation, negative x squared plus 5. And they want me to do an RRAM. I'm going to say this is 2. And I'm going to see if I can create nice, legit rectangles. Let's see. I'm going to say that's 1. I'm going to say that's 2, 3, 4. Okay. They're not super awesome, but they're kind of. I guess before I even continue, guys, how did I calculate the width of each rectangle? I did delta x is equal to 2 minus 0 divided by, how many rectangles do I have? So each rectangle has a width of 2/5. So put a point up here. There is my first rectangle. Here is my second rectangle. My third. My fourth. And my fifth. Oh, thank you. Okay. Do we have any objections right now about this?
Yeah.
What's up? Oh, sorry. First rectangle, second rectangle, third rectangle, fourth rectangle, fifth rectangle. And if I wanted to figure out the area of all this, I would go like this. I need to figure out the height. So the height is determined by the equation. So a lot of you guys on that handout, you guys messed up big time, big time. So here it is. How do I figure out the height of my first rectangle? Negative on the outside. I guess let's figure out these x values. So I'm going to put them in green. This x value is 2/5. How did I figure that out so fast? That's right, guys. Look, the delta x is 2/5. So I didn't have to think anything. This is a 0 over here. My change in x is 2/5, so that has to be 2/5. The next one is 4/5. I know it's 0.8. If you want to write 0.8, that's fine, but there's a reason why I'm writing it like this. The next one is 6/5, 8/5, and instead of writing 2, which is already in there, I'm going to write this as 10/5. 10 divided by 5 really is 2. And there's a reason why I wrote it that way, guys. You'll see right now why. So here we go. I'm going to write my x value, which is 2/5. I'm going to square that dude, and I'm going to add 5. And whatever that is times 2/5. That's the area of the first rectangle. Plus, I'm doing the same thing, guys. 4/5 squared plus 5 times 2/5. That's the area of the second rectangle. Keep going. You guys already know what I'm doing now, I hope. And whoever is fast enough, someone do that in your calculator and tell me what all that mumbo jumbo is. Is that a word? No, it's just mumbo jumbo. There's a whole bunch of stuff. I'm going to take out my calculator too. I have a fancy one that I recently got gifted. I think they gifted me this because they want me to purchase a whole bunch of them for the school, which I'm actually really liking them. Because look how small it is. It fits in my pocket. Look. Hold on, guys. And I can take it with me everywhere. Okay, anyways, I'm doing this right here. Let's see who's faster. Oh man, I'm already behind. Negative. Yeah, I'm already behind. I'm gonna wait for you guys. It would take me forever now. Mazuka, did you get an answer?
No, I have, I can though.
Yeah, get an answer. Did you get an answer, Godinez? Okay. Gonzalez, did you get an answer?
Not yet.
Let me get my TI-84 because I'm used to that one. This is equivalent to saying, let's see, it's equivalent to saying, it's equivalent to saying that, if you think that's easier to read. What'd you get, Mazuka?
I got, oh my gosh, I hope this is right. 13.296. I don't know.
Is that what
I'm
you
like,
got?
double check that.
All right, Gonzalez, what you get? I think it's supposed to be like 8.
I got 7.28.
Everyone's getting something different. All right, I'm gonna take out Desmos. Before I continue, does everyone agree that this in red is the same as what I have in blue? The function evaluated at 2/5 times 2/5, the function evaluated at 4/5 times 2/5, the function evaluated at 6/5 times 2/5, the function evaluated at 8/5 times 2/5, and the function evaluated at 2, which is 10/5, times 2/5. Is that the same thing as in blue? Okay. I'm gonna go to Desmos, guys, because everyone's getting something different, and I didn't calculate this beforehand. So let me go to Desmos, and let me share my screen. Share. All right. I don't care about the graphene, about the graph, but I already put graphene, so too bad. Let's see. What do I want? I want the function. You got the same thing? Oh, then maybe you're right. What was my function? Negative x squared plus 5. And I want a table. So give me a table. And f of x. Actually, I don't even know if I want a table. No, I don't need a table. I think I can just do it right off the bat. Let's see. I can factor out a 2/5. So there's my 2/5 factored out. I'm going to put a giant parenthesis, and I'm going to write f. Oh, man. Yeah, f. Let me open up another parenthesis, guys. open parentheses, there we go. F of 2/5, close it. Oh, that's not how you close it. Plus F of 4/5. Do you guys see what I'm doing? And I'm sorry that we're going slow. I have to push my mouse here. Close that guy. Plus, thankfully, we don't have to do it that many times, 5 times. F of 6/5. Plus F of 8/5. And then finally, plus F of 2. You can put 10/5 if you want. And then shebang. There it is. If I didn't make any mistakes, it's telling me that it wants another parenthesis. Okay, I guess. If I didn't make any mistakes, it's 6.48. Is that what you got, Godinez? Yay, we did it. Okay, so now you see how to do it. It's not too bad. Actually, on the AP exam, they're going to make you do that too. 6.48. All right, we haven't answered the whole question. Look what it says here. Let's see if we can come up with a formula using sigma notation. So this is pretty easy if you're looking at the ones in red or even the one in blue. So it looks like I can do, let's see, what did I do? We started with k equals 1. I want 5 rectangles. And if I look at the one in red, it looks like I can just go f of, let's see, look, 2, 4, 6, 8. And if we don't pay attention to that 2 there and we look at the top, 10 over 5. So it looks like we can say 2k. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So 2k over 5, that will always give me the height. That will always give me this. This will give me k equals 1, k equals 2, k equals 3, k equals 4, and then k equals 5. Now I'm missing one thing. Right now I'm just adding up the heights. I got to multiply all that by what? By 2/5. There it is. We came up with a formula. That's not the only formula. You could also write it like this, guys. Start at k equals 1. You don't have to use the letter k. You can use the letter I or j all the way to 5. Negative, let's see, 2k over 5, close squared plus 5, close that times 2/5. They both mean the same thing. One uses f, the other one uses the actual expression. We still okay? All right. Here we go. Oh, man. I moved a little parenthesis there. All right, here we go. Let's go to the next one. And we're going to go slow. It says, now let's use LRAM and get an upper approximation. And I'm doing the same thing, guys. I'm exaggerating it. Here's 2. And it wants me to use LRAM. 1, 2, 3, 4. Okay, my rectangles are not perfect, but that's fine. Yeah, my rectangles really suck. I'm sorry, guys. My rectangles are really bad. I got a D in art, remember that. Again, my change in x is 2 minus 0 divided by 5, so it's again 2/5. And this time we're going to go, let's see, f of 0, whatever that is, times 2/5, plus f of 2/5, whatever that is, times 2/5. That's 2/5, 4/5, 6/5, 8/5. So all of them except for the f of 2 there. Plus f of 4/5 plus f of 6/5. And then I don't have room for the last one. I'll just write it right here. Oh man. Okay. Does someone want to add that up and see what that number is? Should be bigger than the last number. Does it get an 8? 8 point. Yeah, I think you're right. 8.08, guys. All right. Here comes the big deal. You guys ready? If I am adamant about starting at k equals 1, which most of our integrals are going to start at k equals 1, 99% of them, then what must go in here? Notice that I better get a 0 on the very first one. Perfect. I still write a 2 because all these are still by a factor of 2. Look, 2, 4, 6. So 2, and on the inside I write k minus 1, and on the bottom put a 5. So 1 minus 1 is 0. 0 times 2 is 0, and that will give us that f of 0. Do you guys see what's going on? Okay. Now we're going to see if we can figure these out. I'm going to go really slow, guys. Before I continue, does everyone understand how to read this? Okay. So here's what I want. This is just an illustration. And here's what they're telling us. That we are summing an infinite amount of rectangles. And they're just telling us that we're going to sum from the first rectangle all the way to the nth rectangle. And this right here is your height. And this is your width. Yes. The S of n, that just means that they're summing an infinite amount of rectangles. Well, not yet, because it doesn't say the word limit as n approaches infinity. But that's what we're going to do. The f of ck, that stands for your height of that rectangle, of that specific rectangle. And then the x of c, the delta x of k is your width of the kth rectangle. They don't have to use the letter k, guys. They could also use the letter I, the letter j. These are the 3 most common used letters. 3 most common use for sigma notation. These are the letters that go underneath the sigma. So they sometimes will say the i's rectangle, the j's rectangle, the k's rectangle. Have I lost anyone yet? Not that I'm expecting to lose anyone, but. Okay. And then they kind of, look what it says. All continuous functions are integrable. Integrable. That is, if a function f is continuous on an interval a to b, then its definite integral over a to b to exist. And they have this. So this is the one that I wanted you guys to look at. You see how it has limit as n approaches infinity? They are putting an infinite amount of rectangles. Antiderivative. If they do an infinite amount of rectangles, am I finding the exact area? What do you guys think? Is that a yes? What do you think, Godinez? So if I add up an infinite amount of rectangles, I'm not finding the exact area? The rectangles is infinite. No. Well, it says n approaches infinity. Then yeah, it's exact. Guys, if we approach an infinite amount of rectangles, that's going to be the exact area. Now, something to note. I noticed that I have area above the x-axis and area below the x-axis. If you have area above the x-axis, this is counted as positive. If you have area below the x-axis, it's counted as negative. Chavez, why? Because the y values are negative down there. Now, if there's a question that asks you for the area, just the area. What is the area between C1 and B? Then you don't count the negative, you turn the negative area into positive because it's just asking for area, like the region, how much it takes up. You guys understand that? Don't worry, we'll get to those problems when we get to it. If it asks for displacement, then we do count the negative. Because if you're below the x-axis, that means you're moving left, quote unquote, if it's velocity curve. We'll get there when we get there, guys, so don't worry. All right, I think we've done enough. Oh, now here's where they connect both. And I'm gonna try to, you don't have to fully understand it, guys. You just have to understand the mechanics of what's happening. So right here, this means infinite amount of rectangles. Anytime you see the elongated S, that also means infinite amount of rectangles summing up. That we're summing. That we're summing the infinite amount of rectangles. Okay, I will, miss. I can't right now though, but I will because my phone's not with me. Are we okay so far, guys? The A is the lower limit. The B is the upper limit of the area that I want. So look, let me go ahead and make a sketch. A, B. It's calculating that. Lower limit, upper limit. The f of x is just like f of ck. That is still your height. And the dx is just like the delta x. That is your width. So every time you have an integral symbol and you're evaluating it, this is called a definite integral. Because it's defined. Definite integral. Yes, n is approaching infinity. The number of rectangles is approaching infinity. What it's trying to tell you guys, from the left to the right, you see an equal sign. This is the key. What it's trying to tell you is that this integral, if you see it written this way, means that you're finding the exact area under the curve. Does that make sense? That's all it means. You don't have to say like, well, how did they figure this out? How did they figure that out? All it means is that the summation, that I'm finding the exact area under this curve from A to B. That's all it means. And we're going to go back and forth from the integral symbol to the summation, and then from the summation to the integral. See if we can break it apart. And I'm going to try to start with easy ones. By the way, here's some more notes. You can read them whenever you get a chance. And then there's something called the dummy variable. You can see that right here. It's important, but not so important that like we got to take a whole lesson for that. All it's saying is if I have a to b of f of t dt, that these are all the same. It doesn't matter what letter I use, all the same. They will all have the same value when evaluated. Yeah, it doesn't matter. It doesn't matter with what. You're going to get the same no matter what. You know what I mean? All right. Oh, what happened? Okay, guys. Let's see if we can do some of this. I think example 2 is easy. I think. But you guys will tell me. So let's see what example 2 says. The interval -1 to 3 is partitioned into n sub-intervals of equal length. And here's my delta x. Let m of k denote the midpoint, so they're using mram instead of rram, of the k subinterval. All right, whatever. Okay, go ahead. Well, they said, no, they literally told me midpoint here. That's why they said that. No, that's okay, it's okay. Express the limit as n approaches infinity for this expression as an integral. All right, guys, they're being nice to us because they could have easily broken it down even more, but they didn't. They left it like that. So I want you guys to just circle this, that m of k. That just means the x value of your kth rectangle. That's what this means as well. Both of those mean that. That 4 over n, that's just your delta x. This I can turn into an integral really quick because they're being nice. Integral, here's my interval. Lower limit, -1. Upper limit, 3. Notice, I want you guys to notice that the difference between 3 and -1 is 4. So check mark, it works. And this is my equation. So this is going to be 3x squared, because that's just some x value, m of k, x value of the k's rectangle, minus 2x plus 5. And that 4 over n is just your delta x, dx. And I guess technically I should be doing that. So you can determine what's width, what's height. Do you guys feel okay? Okay. There is a common practice, so let me just warn you guys ahead of time. They don't always put the parentheses in math. They don't always put the parentheses when they're doing integrals. I just want you guys to know, relax, don't freak out. This is the start of your integral. This is the end of your integral. It is not dx times 5. It is all of that times your delta x. This is what makes your integral your integral. It's f of x times dx. Now, when they were doing antiderivative, the dx goes away because those are just properties of how do you get your antiderivative. But it's in there. If the dx does not go away if we're doing sigma notation. If we're doing sigma notation, we're constantly multiplying by that dx, whatever that is. Okay. What's up?
I thought you said, like, when you said it starts at -1.
Uh-huh.
It wouldn't end at 3.
Yes, I'm talking about where does the integral start and end, like the expression. The expression, not where.
Like if you're saying f of x is 5, you say it starts at f and ends at 5.
Yes.
Okay.
The expression that we, because a lot of people just do this.
I didn't know.
All right, don't write this down, just listen, guys. A lot of people just do this and they forget to put the dx, and I understand why, because they're just going fast. Oh, antiderivative of that. Well, without that dx in there, now it's a real integral, because a lot of people go like that plus, and then they have another integral, like, okay, no, you can't do that. You got to end the integral. That dx ends it, and that's how we know, like, oh, okay, we stop. That's whatever's inside between the start and the dx, that's what your f of x is. So I just meant like the end of the expression, the end of the integral expression. Okay. Let's see if we can, oh, this one might be hard for you guys. So we'll come to that one later. We'll come to that one once we do easy ones. So let me see if, okay, example 4 is an easy one. And we're going to do it with RRAM. Because I think RRAM is the easiest for everyone. You guys ready? I want to turn this into sigma notation. So think about it. Let's think about it. So first, let's find a delta x. The delta x, what is my upper limit? What's my lower limit? Do they tell me how many rectangles? Yeah, they don't tell me rectangles, so we're going to write n. So your delta x is 5 over n. Okay, now just like example 2, where I told you that's just an x value for the kth rectangle, I'm going to do the same thing here. I want the x value for the kth rectangle. Well, if I'm using RRAM, I start at 1, and I'm going to add, let's see, I'm going to add k times delta x. Does that make sense to you guys? No? Okay. If I want my first x value, don't write this down, just listen. This is 1 times a change in x, so my first x value is going to be 5k over n, but I don't know how many rectangles I have. So this is like my delta x, 1 plus your, because I'm doing RRAM.
Oh, okay.
Maybe I should do a visual, and that will help you guys. No, but everyone else, you know what I mean? Let me do a visual. Don't write this down, guys. Just listen. Wow. Okay. Here's my visual, guys. Here's 1, and I'm going to say here's 6. The easiest way for you guys, I'm going to say, don't write this down. Just listen right now. I'm going to say n equals 5. If n equals 5, that means my change in x is just 1, right? And let me write everything in blue that I'm doing. And I'm going to erase everything in blue in a little bit. So let's see. 1, 2, 3, 4. 1, 2, 3, 4, 5. Perfect. Here it is with RRAM. My first rectangle, my second rectangle, my third rectangle, my fourth rectangle, my fifth rectangle. Are we still okay? What is this first x value? Well, that first x value is a 2. So don't write this down. I'm just trying to get you guys to see if you guys can figure this out. My first rectangle is a 2 for RRAM. My second rectangle, the 2 means the second rectangle down there. The second rectangle is a 3. The third rectangle is a 4. The fourth rectangle is a 5. And my sixth rectangle is a 6. Now, how do we get to this? Well, I got that 2 by doing 1 plus the change in x. How did I get the change in x? The change in x is k times delta x. How did I get the 3? Well, if you think about it, if you go all the way to x1, 1 plus k times the change in x. It works, guys. That's a 2. That's my second rectangle. 2 times 1 is 2. 2 plus 1 is 3. Do you guys see how we're doing it? Don't write this down, just listen. 1 plus k times change in x. 1 plus the kth rectangle, this is my third, times 1. 3 times 1 is 3. 3 plus 1 is 4. That's how I got the 4. K is the rectangle that you're in. 1 plus k times delta x will always give you your new x coordinate, because all this is doing is just counting how many rectangles you're going, first, second, third, fourth, and then you're changing x. So that times the change in x will tell you your new x value. Does that make sense to everyone? Okay, so now that we've covered that, I'm going to erase everything in blue. And I'm going to go slow again. Where's my little, oh, here it is. Yeah, these can be tough, guys. Good thing there's only about 1 or 2 of these questions on the AP exam, but we're not testing to the test. We want to make sure that we know the concepts. Okay, so here's what I'm trying to tell you. That you can figure out, I'm going back to red. You can figure out where you are at, any x value for your kth rectangle by doing this always. A plus k times your change in x. I'm going to give you formulas. Don't worry. What is a? The a is always the lower limit here. The lower limit starts at 1. So here's your x of k. 1 plus k. And your delta x is 5 over n because we don't know how many rectangles we're going to use. So write it like this. You like to have the k on the right-hand side. So 1 plus 5k over n. So now I'm going to do this. Limit as n approaches infinity. And we're going to sum. I start at k equals 1 because I'm using the letter k. We could use the letter j or I. All the way to n. And infinite rectangles. Open parenthesis, the expression is x squared. This gives you your x. 1 plus 5k over n. Close it, that's your x. Square it. Open another parenthesis, 5 over n, close. That's your delta x. Okay, I think we did it. Don't worry, we will go back to example 3, but I think we still need more practice. So let's go to example 5. Let's see if we can figure this out. We're going to do RAM because I think RAM's the easiest for now. Once we become pros, we'll start doing M and L. All of them will sum up, if I'm adding an infinite amount of rectangles, all of them will sum up to the same number. All right, so here we go. Delta x. 2 minus 1 divided by the number of rectangles that they tell me to do. The x value of the kth rectangle. Start at 1 plus k times the delta x Chavez, where did that one come from? See the picture below or before. Here we go. Limit as n approaches infinity. That's an n, not an h. You could also say delta x approaches 0. That's the same thing, guys. K equals 1 all the way to n. Square root. What is my x? This is your x right here. 1 plus k over n. Close it. And then outside the square root, 1 over n. Put that in parentheses. There it is. These two are equivalent now. All right, let's see. Let's see if we can do this again. Delta x. 6 minus 4 over the number of rectangles. 2 over the number of rectangles. That's your delta x. The x value of the kth rectangle. 4, we're doing RAM. All of these are RAM. 4 plus k times the delta x, 2 over n. So 4 plus 2k over n. I'm ready. Limit as n approaches infinity of k equals 1 all the way to n of ln of 4 plus 2k over n, 2 over n. Yeah.
K is the rectangle.
The rectangles.
N is the number of rectangles.
N is the number of rectangles.
So you gotta K equals 1 even if it says like the interval is infinite.
Because I'm using RAM, yes. You know what I mean? If I had to use LRAM, then I have to either adjust the K or I have to adjust, just like we did last time, K minus 1 if I'm adamant about starting at K equals 1. Okay. Don't worry, we're going to show you guys some examples in a little bit. All right, here we go. What do you notice about this one? This one counts what? Backwards. Delta x is equal to 5 minus 7 divided by the number of rectangles, so negative 2 over n. You're still going to start at 7, but you're going to count backwards now. Your k rectangle, if you want to keep it as your quote-unquote formula, is 7 plus k times the delta x. And notice that's where it'll force it to be negative anyways, 2 over n. So 7 minus 2k over n. The k is just the number of rectangles. The rectangle that you're in. Here we go. Limit as n approaches infinity. And since we keep using k's, k equals 1 to n. I'm going to open a giant parenthesis, 3, little parenthesis. I'm going to write 7 minus 2k over n, close it, plus 1, close the giant parenthesis. And then all that times your delta x, negative 2 over n. So hopefully by now they're getting a little fun. All right, here we go. Last one. I need my change in x. 3 minus 1 over n. So 2 over n, where n is the number of rectangles. If they told you that they're only using 2 rectangles, then your delta x is just 1, which makes sense. The x value of the kth rectangle, 1 plus k times your delta x. So 1 plus 2k over n. Here we go. Limit as n approaches infinity. Sum them up. Start at 1 all the way to n. 4, I guess open up a giant parenthesis first. 4, little parenthesis, and then type your x of k. 1 plus 2k over n. Close that little guy. Plus 2. Close the big one. Oh, yeah. I would have gotten it wrong. I need to put a square on it. There we go. Now it's right. And then I multiply that by your change in x. And it works, guys. If you want to put like 1, 2, 3. If you want to put 2 rectangles, put n equals 2 and erase the limit and see if it works. And it works. It's going to be RRAM, but it works. All of these are RRAM. We're using RRAM. Okay, let's go back to the one we didn't do. All right, let's see if we can figure this one out. Don't worry, guys, we're almost done. Let's see. Change in x. 7 minus 4 divided by the number of rectangles, 4, 5, 6, 7. So 3 over n. The x value of the kth rectangle. I start at 4 plus k times the delta x, 3 over n. 4 plus 3k over n. Here we go. Limit as n approaches infinity. That's the number of rectangles. And I'm going to sum them all up from k equals 1 all the way to the infinite rectangle of 4 over, let's see, 4 plus 3k over n. All that plus 4. Giant parenthesis on the whole shebang. Times 3 over n. Ooh, I should have put that one last. Because it's probably a bad one to do right off the bat, like to be the first one. You know what I mean? And there it is, guys. If we were doing LRAM or MRAM, it would be a different story. All right. I want to go over the handout. I'm just going to do a few of them with you guys so you guys can see it's not that bad. So take some time right now to go. If you haven't printed it out, no big deal. Just write it with a pencil. But if you want to print it out real quick, go for it. I'm going to take out the handout, guys. So I'm going to go look for that. Oh, these are all Raymond sums. All of these are Raymond sums that we're adding up rectangles. These are all Raymond sums, guys, because we're adding up rectangles. And I'll wait for you guys to all come back. Okay. I'll give you guys another minute because I can see some of you guys left. All right, guys. Once you see patterns, you're going to be able to do this one really fast. I don't want you to become a little robot. Please, please, please. Yes, there's patterns, but make sure that you understand the concept. Are we clear, guys? Okay. Here's how you're going to do it. I'm going to do a few of these. As a matter of fact, don't give me work. I would work right to left, not left to right. So give me a letter between A and J. It does not matter which letter, any letter. What letter?
B.
B. Okay. So here's what I would do. Start off, you see that 3 over n? So you know that your delta x, or the B minus A, you know that whatever the difference is in the top, you know that B minus A has to be a 3. And you know, these are all RAM, all of these are RAM. You know that it has to start at 2. Do you guys see that? Oh, because I typed them out. Plus it says it there. Does it say? Match the integral expression on the left column with the appropriate limit of a Raymond sum on the right column. Oh, it doesn't say. But they're all RAM the way they're written. On the AP exam, I think I have yet to see any that are LRAM or MRAM. They have all been RRAMs. I don't know if they're doing that on purpose. I'm gonna find out. I'm gonna ask a professor. Like, why have they all been RRAMs? All the ones in the AP exams that I've seen, all of them have been RRAMs. The LRAMs and MRAMs are harder. All right, look for a starting at 2 and ending at 5. So 2 and 5, maybe that one. Notice that there's a square. So this looks like 4x squared plus 2. So look for that, 4x squared plus 2. And starting at 2. And ending at 5. There it is, number 6. 4x squared plus 2, starting at 2, ending at 5. So number 6 is letter B. Give me one more. Give me one more, Godinez. Gonzalez, give me one more. One letter.
F.
F. Okay. I start at 3, but notice there's a negative here. So I'm counting backwards. So I'm going to go backwards 2. So start at 3, ends at 1. So look for one that starts at 3, ends at 1. There's only one. So it looks like it's this one right off the bat. But let's check it. This better be 4x squared plus 2. 4x squared plus 2. There it is. So letter F is number 8. Do you see how we did it? Yep. It's a negative 2 there, guys. That's how we know it's going backwards. You're counting backwards. Remember, the lower limit is the start. The upper limit is the stop of the area. All right. Finish this handout out first, guys. And then once you finish this handout, see if you can tackle the delta math for more practice. Oh, you know what? Let's do one together on delta math because I feel that we have to. So stay there. Let me take out the delta math. Okay. Where does it say Raymond sums? Raymond sums. It has a visual too. I love that. So too many. Oh, that's fine. Let me zoom in. No, too many. Give me less rectangles. There we go. One with less rectangles. Okay. Let's see if we figured this out, guys. It says, let F be the function graph below. If 10 subintervals of equal length are used, write a summation that would represent a right Raymond sum approximation of 1 of 3 of this function. Okay. Well, first of all, I have 10 rectangles, so the top number here must be 10. How can I type numbers? Okay, let me get my little keyboard out. Number 10, 1, 0. Okay, and then I'm going to start at 1. So I'm going to put a 1. And I'm going to add, let's see, I'm going to add your delta x. So that's going to be k. What is the change in x, by the way, on this one? 3 minus 1, so 2 over 10, which is 1/5. Did I say that right, miss?
I think so, yeah.
Okay. 1. And where's the division symbol? 5. Let's see if it did it. And I'm going to type in there, what am I going to type? K over 5. And K. Yeah, K times 1 over 5. So there it is. If I am wrong, well, forgive me, but let's see what happens. This is the first time I've done it, guys. So I don't know. I just opened it up and just tried out. Is it right? Or how come it didn't? Your summation is correct. Oh, yeah, okay, yay. Look at this, guys. This is so awesome. It tells you the kth rectangle. It tells you what it's adding up. It's doing f of 1.2 times 0.2. That's your delta x. And it's telling you the number times 0.2, and it's telling you the area of the first rectangle. This is so, you don't think this is awesome, guys? I think this is so cool. Look how awesome this is. This is the first time I've ever done this one, guys. So I'm just freaking out how cool, how smart that this person is to have programmed all this. Look how long do you think it took him to program all this? For those of you that are programmers, this is sweet. Look at what the Raymond sum is. Your summation is correct. Press submit for credit. Oh, okay. Submit. Are you sure you want to submit? Yes. And there's your little check mark like you always get. I love it. I love it, guys. I think this is awesome. I love the visuals. So that's what you're doing on Delta Math. I think that's going to help you all big time. And yeah,